Okay, last group of problems from this unit are deal with powers. So you have this equation on your equation sheet, and the equation deals with the theorem exactly the way it looks in part A here on number 20. So to use the theorem, you take your R value to the power you're given, and then you multiply your thetas with that power as well. So here is how that looks in this form. So 3 to the 4th, so R to the power, and then cosine of 4, and I'm going to write 4 as 4 over 1 times pi over 6, plus I sine of 4 over 1 times pi over 6. And there you have applied the theorem. Now we do need to do some work here to pretty this stuff. 3 to the 4th is 81. This 4 over 1 times pi over 6 is 4 pi over 6. And we can reduce that to 2 pi over 3. Kind of nice when you're working with complex numbers in polar form, because when you do that work with your first theta, it also applies to the second. Of course, I would have to write it correctly. There we go. Now, it says that they want the answer in standard form, and standard form is A plus BI. So we're not quite there yet. We do need to do our unit circle values here for cosine of 2 pi over 3 and sine of 2 pi over 3. Cosine of 2 pi over 3, cosine at our thirds, at our pi over 3s is 1/2. 2 pi over 3 is in the second quadrant, so cosine is negative. Sine at our pi over 3s is radical 3 over 2, and 2 pi over 3 is in the second quadrant, so cosine is positive. Or sorry, sine is positive. Since we have fractions, I'm going to go ahead and make that 81 over 1 for when I multiply this through. 81 is not divisible by 2, and we are asked for exact values, so I'm going to write my final answer as negative 81 halves plus 81I radical 3 over 2. Not the prettiest answer, but it's our answer. It's in standard form. So that's the most basic kind of power that you can deal with. This next example, we're asked to find the indicated power using De Moivre's theorem. So what we need to do is put this into polar form and then apply the theorem. So negative 1 plus I. We need to identify our A and B. A is negative 1. B is positive 1. So we're going to go through the same process that we did in number 17, where we turned our complex number in standard form into polar form, and then we can use the theorem. So to find R, we do square root of A squared plus B squared. And that's going to give us square root of 2 as our R. Theta, we do arctan, and we're doing B over A. So tangent is 1 at our fourths, but if we have a negative A and a positive B, if you think about kind of how that quadrant would work, negative A, positive B, we would be in quadrant 2. So our tangent fourth in quadrant 2, we're looking for the angle 3 pi over 4. And now we can put our complex number into polar form. So our complex number in polar form is square root of 2 cosine of 3 pi over 4 plus I sine of 3 pi over 4. And we're doing this all to the third power. You may be thinking that was a lot of work. I could have multiplied 1 or negative 1 plus I to the third power. I could have multiplied that out quicker than I can turn this into polar form and use the theorem. And that may be the case for this example. It's good to practice just in case you have to the 8th power or to the 6th power like you do in the next two examples. The theorem is definitely more useful and quicker the bigger your powers become. So let's apply the theorem. We're going to do radical 2 to the third power. And then we're going to multiply our 3 with our angles. I just go ahead again and rate that 3 as a fraction since everything else is a fraction. Square root of 2 to the third gives us 2 radical 2. And with fractions, we just multiply across, so 9 pi over 4. We are looking for our complex number answer. If we were looking for our polar form answer, we could be done here. You could also, I think Math Excel made you change 9 pi over 4 into the coterminal angle. 9 pi over 4 is coterminal with pi over 4. We subtract 2 pi there. We do want the complex number answer though, so we're going to do 2 radical 2 and cosine of 9 pi over 4. Again, that is coterminal with pi over 4. So cosine of pi over 4 is radical 2 over 2. Sine of pi over 4 is radical 2 over 2. Every once in a while in trig, we do a problem with like 5 million 2's in it, and this seems to be one. All right, since there are so many 2's, I'm going to be really careful on this next step and write it out. 2 radical 2 times radical 2 divided by 2. 2 radical 2 times radical 2 divided by 2. And see what we can cancel. Our 2's cancel. Square root of 2 times square root of 2 is 2. Same thing in our second term. Our 2's cancel. Square root of 2 times square root of 2 is 2. And we need that I. Like I said, I don't think that may not be the fastest way for you if we're doing to the third power, but it definitely is going to be faster when we're doing a problem where we have to the 6th power and to the 8th power, like our next two.